Okay, so now we have Rafael who's going to talk about dust-gas-planetesimal interaction in white dwarfs debris disks. So you have 15 minutes. I will let you know 3 minutes in advance.
Thank you. Hello there. Well, my work is also obviously with Beck, that is my supervisor, and Dimitri, that is not here, but it's also an important part of the project. I have seen that every disk that we have seen here are quite big. In this case, we are going to really small scales into white dwarf debris disks. And for context, these debris disks are basically made from destroyed debris that is surrounded the white dwarf, like Kuiper belt objects that get too close, get disrupted. And so you create this disks that are mainly made from gas, dust, whatever is around, mainly, I mean, those two things, obviously, that we can find those components with different observational signatures. We can also find planets, but there's no like confirmed planet, I think. There might be one, but it's complicated. It's not one direct way to find them. So we'll get to that maybe later. How do you find this? Well, you can find gas emission, especially the most famous one is the causes 2 triplet. And obviously with infrared access, you can find also evidence of dust in these disks. We have found more and more over the years, well, the observers side, most of the disks show infrared access, and only a few of them show gas. So we're talking about disks that are mostly dust-dominated more than the protoplanetary disks that are usually the other way around. And the observations have also shown interesting behavior, such as flux variation over any time scale, so the decades, over years, over months and days, and even over a few hours. So that we don't really understand what's going on. And also, they show non-axisymmetric geometrical structure. This is not a direct image because it's impossible to directly image them. Instead, this is a Doppler tomograph. If you're not familiarized with them, it's just the velocity map in the velocity space. So it's like this is kind of, this is the outer part, and it's hard to interpret them sometimes. But this profile shows that it's definitely eccentric. So this is like kind of to a scale the debris disk next to solve them in one image. It's like taking an image from part. On these disks to study in detail the gas-dust-planetesimal interactions in these extreme environments. Now, as I mentioned, these are dust, most of them are dust-dominated disks, but we can also find gas-dominated ones. So we wanted to be able to explore all that parameter space. And how to do that is not straightforward. The simulations kind of break at the beginning. So we found at least 2 solutions. The first one with Cristiano is that while using individual time stepping, you can calculate the stopping time of the particles with this equation. And usually for gas-dominated ones, you just use the density of the gas. But for dust-dominated ones, we realized you can basically invert the approximation, and it works quite well. But the other approach is thanks to Daniel's recommendation, is if you use global timescale time stepping, you can use implicit scheme for the dust gas drag. And that also works very, very well. And you are not using any approximation in the stopping time, so it should be more accurate. Although this one is a bit faster. But this one allows us to even go to dust to gas ratios that are not really observationally I forgot that word. Well, we have not seen any dust to gas ratios of like kind of one, you know, but it's usually one or the extremes. But with that one, we can actually do that, and it's fun to explore that. So if we look at our space simulation, obviously we take this setup. So it's just first at the beginning, an axisymmetric flared power law surface density profile, and we're using two fluid simulations with just one dust, one size of dust. And for the parameter space, just a few parameters that are important. The mass of the star is going to be 0.6 because it's like the average one. But obviously the spectra for the observables that we are going to try to reproduce is going to be a wide dwarf spectra. This parameters, the mass is really low mass because we're talking about this that is made from Kuiper kind of like objects. So it's really low masses. The inner and outer radii are really going to be in the solar radii scale, so really small, as I have said. And I wanted, and thanks to Enrico now that he pushed the eccentricity this setup, we can now explore the eccentricity option, and because it's really motivated, that was the word, motivated, for the radii to be eccentric, since they come from mainly disrupted planets from very far away. On that size, also explore some different dust sizes, and we also want to include planets from either small Ceres mass objects to, why not, a massive Jupiter planet. In this case, in these simulations that I'm going to show you, I just chose a location from them and an eccentricity. So let's start with just the case of a circular disk and eccentric planet. I'm going to show you only 4 simulations. That is because I could show you many, but it's just to show that we can do this. Are the movies reproducing that? Can I do both? Yes. So it's just to show that in the case of circular disks, you can kind of see the planet over there, but not that much really. And both work. We are avoiding any numerical clamping, numerical problems. This is not the density, the column density, instead is the midplane. And I forgot to put on the time, but the time is at the end of this simulation is around 15 hours. There's really short time scales also. It's really tight orbit. So this is the case for circular disks with eccentric massive planet. Wait. And how do I go to the next slide? There we go. No, that was in case the movie didn't work. This is the last time scale time output. As you can see, many structure in the dust from the eccentric planet interaction that I find quite beautiful. But now we can also have eccentric disks, both gas dominated and there we go. Both dust dominated and gas dominated. And we can see a lot of structure going on. So I love it. It's been a long time until I finally got this observations simulation. So what can we do with these simulations is the most important. So let's take one of those 4 that I'm not gonna say which one was it, and we can take observables comparable to the ones that we know we can take from them. So the first one is the Doppler tomograph, and we can see that it shows not a circular velocity map, so it must be an eccentric disk. The lighter, I think I might be doing it wrong, I don't know. So I need help from Sol or somebody. But but I think I figured out how to do the SED correctly. So, but I still want to double check with you. But definitely we can see that it has some dust, but we have no point of reference to is this dust dominated or gas dominated. So I'm just gonna tell you, it was the dust dominated disk with an eccentric dust dominated one and eccentric disk. So this goes to show that we can now reproduce almost any disk that we want around the white dwarfs. We need to just set the parameter space that we want to explore more accurately that we can already have. And we can take observables from them that are comparable to the ones we know we can get from these disks. And so now we want to hopefully match them, right? And so just as a summary, I don't have any results yet, but we do have a lot of questions and directions for the next steps on this. So and some immediate future work. Thank you. So immediate future work is we really want to explore more in detail the dust to gas ratio, because I think it's a really novel thing to do in these simulations. Explore more on the dust grain size, planet interactions, and maybe even the geometry with different sizes and maybe more ring-like structures. And obviously, after getting all those simulations right. So thank you all for your attention. Any questions?
Question again, which is yours first? Come on. All right. Okay.
I was wondering, so you showed the dust size, but I have no idea, like in the context of white dwarfs, what kind of scopes number are we speaking of? Is it like thousands or?
Very good question. Well, we're kind of like, we don't know really from observation that we cannot estimate accurately any dust population of any of the disks that we have found. So we have a lot of freedom there to explore. In these simulations, the Stoke number is kind of 10.
10?
Yeah. Yes, it's 12 something.
Questions in the room?
So,
No,
sorry.
Chris here.
Jose.
Do you know what causes these little flashes in your animation?
No, but I mean it's just V mean and V max that like the colors of the limits of the color scale that I always get them wrong. Actually need help there. So,
Enrico?
Yeah, so the question is like, do you see any special features that in the dust? Like, I mean, besides like a linear, like circular motion, do you see some like a dust planting or it's because you know there are like some structures that have been associated to like horseshoe features that actually occur also in eccentric disks, and it was a big question whether like these type of structures actually capture and collect dust grains, like acting as dust clouds. So I was wondering, since you actually did it with the dust, whether you saw this type of clustering of dust particles.
Just for people online, the question is if there is any kind of clustering or gathering dust in certain parts of the disk in these simulations.
Great question. I would say that I haven't run enough and I haven't analyzed them really in detail. Most of my analysis have been more in the are they actually running side of things. So now that's why now is like time to sit down, run the proper simulations that we want and analyze them properly. But I'll have that in mind, actually.
I have one question myself. Do you think that eventually we'll be able to tell if it's closer to a dust to gas ratio close to 1 or something more gas dominated? I mean, do you think you can create a whole set of observables based on your simulations and then compare that against observations? Do you think that's doable?
That's one of the main objectives, like to create a repository of possibilities. So if you take an observation, you have like, okay, maybe it's more in this side of the parameter space. Hopefully, yes. Yeah.
That's your goal.
That's my goal. Yeah.
Did you check for time variability of your SED?
So time variability in the SED.
For example, disk where you can have dust that gets closer or farther away from the star, so it changes temperature maybe.
I want to do that, but that SED that I showed, I ran it last night.
Okay, perhaps one last question, if any.
But yeah, I want to create movies of the SED. It's gonna take forever, but I think there's a lot to explore there.
Last question.
Maybe a bit more general question. Do you also account for turbulence in your disk? Because I heard it's also, and usually the vortices in the turbulence that really traps the dust. Is that true? I don't know.
Yeah, I'm lost.
Do you model that in your, as in, do you drive any
A specific, I don't know.
or you just let it,
I run it the usual way.
so there's no additional input to other dynamics in your disk?
Not yet,
Okay.
but we cannot want to at some point add more physics to it. But so far it's been the kind of standard disk setup.
One more question. How do I model that cat in the disk? Can I put that in the simulation?
Well, it would be great.
It's a nice option.
If you have a setup for that cat, please give it to me. Thank you.